Good afternoon, everyone. I'm Jonathan Waller,
I'm Jamel Sylvester.
I'm Felicia Nicola.
and this is our first monthly update on our project progress. So, our general problem statement, we're basically working on dialysis in a developing country. So, we're really limited by the resources and what we can do as far as like cost, and that's the main thing we're trying to address is lowering the cost down and also trying not to use things such as external power sources and also consider water limitations.
So some of the refinements that we've made to our problem statement as like this past month has gone on is we're trying to minimize cost specifically and also minimize waste in regards to our PD solution.
So essentially, we have planned that before spring break, we should have a SolidWorks drawing or model of what we want to do. So after spring break, we can begin prototyping and designing and testing it out.
So the work completed that we did in the month of January after I guess Christmas break was we designated and set meeting times for this whole semester, which was kind of a job in itself on working through three people's schedules. We had a shift in addressing on what we're trying to address on the dialysis problem after talking to a dialysis patient, and they told us that one of the biggest things that run up the cost for PD in the home setting is that there's a lot of waste as far as they order the materials in bulk, but those materials in themselves have a shelf life, and they end up throwing a lot of it if it doesn't get used within the month that they order it. We're still working on the customer discovery and stakeholder analysis. After we're gonna still kind of plan to talk to maybe one or two other dialysis patients that do PD in the home. Individual sketches, we have done, I guess, like loose hand sketches of how we potentially want to address the problem, as far as maybe like the layout of our device or how we would like to improve upon the, I guess, standard PD device at home right now. And we had kind of change in like how we plan to filter the solution. We'll see in the next slide.
So more future work that we need to do. We want to continue developing our stakeholders. We want to talk to more dialysis patients as well as people in industry to see specifically what needs to be modified. We want to talk to more dialysis patients, generate materials, list for anything that we need for our prototype, as well as just basically validate our hypothesis that it's the waste solution itself that we need to work on.
So like some of the research that we've gone, so we like Baxter has a machine that kind of takes a concept that we were working on initially, but basically that idea of lowering the cost of solution. So they take water from a sink and then they funnel it through a tube and then to a machine which mixes with the peritoneal dialysis concentrate, and then after it comes out of that, it's a solution like the peritoneal dialysis solution. So with that, we were trying to find a way to take maybe water that isn't purified and isn't filtered and filter that with minimal resources and also with that external power. So we were thinking about maybe incorporating UV light, but with that also for the filtration process, there's things out there that may take the first step in water filtration, and those are water purification tablets. So there's some already out there. There's Aquatabs, Aquamira, Tahamayan. It's not a brand in the United States, but some of those things that once the water is purified, we have to consider is the ionization of the water, also the biocompatibility, because a lot of times those tablets contain chlorine or iodine, and that's how they purify it, and then also like long-term exposure to chlorine and iodine in the body.
And we have talked about maybe reaching out to Baxter to talk about the device that they have in the home setting that can filter the water and also add the PD solution. But they just started the clinical trials at the end of 2018, so we're not sure if they can talk too much about it, but they're pushing it towards going towards the market very soon. What is the questions that we are addressing is what is specifically in the PD solution. So basically it's just sugar, water, But as we learned from Baxter, that you're able to break that down into having the water separated and having the a highly concentrated solution of the PD, and that you can later add that to water itself. And we think that will be a good thing to consider in our project, because a lot of the shipping cost is due to the water weight. So if we can just think about shipping the highly concentrated solution by itself and then adding the water from home, that would also cut some cost for the patients. And can it be made at home? Yeah, it can obviously be made at home just by adding the water, but we also have to consider user error about how much of the highly concentrated solution should be added to the water. And the technology that exists right now, we learned that there's 3 big devices, one that uses UV light for as like a whole PD I guess machine itself, but also the Baxter one, and then we're considering both of those designs for ours.
Some of the challenges that we face finding information for sterilizations, obviously there are going to be FDA regulations or some kind of regulation as to the concentration of the fluid that can be put into the body, like what types of materials can be in it, what concentration that's acceptable. So just trying to find that information is a challenge that we face. We've also trying to figure out like how to sterilize the solution, as well as getting in contact with companies. We keep reaching out to Baxter in particular because they're the leading company right now in the dialysis field, but we haven't heard back from them, as well as testing methods once solution is created. So how are we going to go about testing whether our design is effective or not?
And earlier this month, we were really considering a way like we can just basically recycle the fluid after it's been used, because it's basically like urine, and we thought maybe we can just remove the salts and stuff like that from it. But there's like no information on doing that, because it's kind of not a thing to reuse things in the medical industry like that, because you're basically putting toxins back into the body if everything's not removed. So we're kind of moving a little bit away from that because there's no information on it and nothing we can really do research on ourselves about it.
So our February objectives are having a final mock-up concept and drawings and sketches, and that's also CAD and SolidWorks. And then develop ideas for validation testings of our prototype and feasibility of them. And then lastly, like having a lab space booked, and so we can actually have tests in regards to being able to support all of our hypotheses and claims.
And here's our budget as of right now. How much we spent was $100. And right now, all the supplies you see above are basically going to be used for our mock-up that we're trying to build later on this following month. Questions?
Questions or comments, suggestions? So just reorient me a little bit. So in terms of your central or did you have your problem statement?
Yeah, general problem.
Okay. And so in terms of how you're planning to address this general problem, you're focused on a new...
Reducing costs, but then we plan on reducing costs by trying to reuse peritoneal dialysis or like PD solution. We're trying to find a way to like purify the water that's going into the PD solution.
But we're not planning on like making a whole new device. We're thinking of like probably improving upon the basic PD that's used right now, using the same pretty much materials, but obviously like kind of changing the procedure on how you would, I guess, prepare the PD solution itself.
Okay. So in essence, your general problem statement is that dialysis in developing countries is too expensive.
Mm-hmm.
You're trying to your concept is you're trying to find a way to reuse the PD solution, and that's going to bring down costs.
Yes, either that or find a way that the user can prepare the PD solution in home, so they don't have to have all that shipped out to them.
And what are those costs? What does that look like for the user?
We don't have it in this slide, but we had it in our last presentation. But we pretty much can save the user from wasting money, basically because they thought some of the solution if it's not used within a certain time limit. So basically we're thinking if you can make it as you go, you really eliminate that whole thing of throwing out the solution.
So currently about 52% of PD's cost is due to the actual solution itself. So if we can find a way to reduce how much they spend on a solution, then we can drastically cut down the cost of dialysis.
And so at this point, your alternative approaches, you're looking at potentially, you said a home mixture, and that's where the tablets are coming in for water purification. And then what was the third? What was the third one?
So we're looking at making the solution at home. So we have three: making the solution at home, or finding a way to recycle the solution, or even possibly like a service type business where we find a way to reduce the amount of solution that they order. Because essentially, the patients, they end up ordering more solution than necessary because they're scared of running out of solution because they only get one order a month. So after that month, they can't order anything else until the next month. So they always order more than necessary, and then it expires and goes to waste. So maybe finding a way to minimize that as well. So we're just looking at those three options.
Gotcha. And then in terms of your, can you show me your timeline one? So so it sounds like you're still trying to decide on the concept for the solution. So when will the concept decision be completed?
Probably by the end of this week. We're trying to get it done early February.
Okay. And then you work through the rest of the process of alternatives and criteria constraints for your solution.
Yeah.
Okay.
What
Other question?
Yeah, what about adding like a preservative? I mean, you said it was basically sugar water, right?
Yeah.
They keep like Sunny D and all that shit shelf stable for months. So like, why couldn't you add, I don't know, like vitamin C or something or whatever to?
You probably could consider that for like design.
Yeah, I think whenever we incorporate a preservative, we have to think of like long-term effects on the body because we're like filtering out all the blood. So like we could like see if there's any research articles on it. It's just like whatever we add or like change about the solution, we have to think of like this is going to be constantly in your body and like long-term exposure.
And also if we can test it ourselves, like we kind of limit on what we can test here.
Yeah.
If it's safe for consumption, I guess.
All right, thank you very much. Volunteers.
And only Coke.
Go ahead.
That's all.
You can say you sick.
Oh my God.
All right, you ready?
Yeah.
Go.
Hello, my name is Shannon Mitchell,
I'm Max DeLeon.
and we are the replacement makers.
Okay, so the general problem statement, it hasn't changed much the last time at all, I believe. It's basically the medical mannequins used today do not act as realistic simulation of the modeled procedure. Instead, they are used solely to repeatedly practice the procedure. So the main thing is to help medical physicians and doctors practice doing a chest tube insertion before they actually get to the patient so that they're prepared in that moment.
So we have our criteria and our constraints. So our constraints is that the stiffness control fluctuate between 0.2 MPa and 0.8 MPa. They cannot be more than Cadaver price, which is $110. It cannot be hard to apply the synthetic skin to the medical mannequins. And then the adhesive cannot affect the longevity of the mannequin. The criteria is that it must be biocompatible. It has to be composed of a porous material so that it can be as realistic as possible. It must match or be within 90% of elasticity measured from the cadaver skin once we get that in. And it must be adaptable to other medical procedures. And then we still have it as cell culture friendly.
This is an image of our timeline. So far we've gotten the 3D printed frame.
Can you see it? We've done the 3D printed frame. We visited.
We visited Dr. C. We visited Dr. Joyner in Chapel Hill, and we drafted a protocol.
And then this past Friday, yes, we met with Dr. Joyner at UNC Hill, our first time meeting him face to face. During this meeting, we basically went over what our project was. He showed us examples of medical dummies, one of a child and then another of an adult male. And we saw how they actually latched on to how the skin, how it felt, and how it actually latched onto the mannequin. So it was very helpful in doing that. So we identified the specific area where we actually want to have the chest tube insertion and where it should be a mannequin. So he described that it should be the intersection of right below the nipple, drawing a horizontal line, and then the intersection of where it is if you draw like a straight line down your armpit, basically. I'm not sure about the technical words. And another thing that he mentioned is that it has to be a big enough size, a third to a half of the body torso, in order to actually so the doctor can actually go in and do the chest tube insertion. And then it was also important that we identified the areas of improvement in the mannequins. Blending the skin with the actual mannequin, he mentioned, was a distinct problem that he has seen in his experience. And then also the different diverse pigments, usually they come in the same tannish color, and they don't account for the different skin tones that are inside of our population today. And then lastly, he advised that we do, stay simple with the skin and don't try to do the many different layers, but we focus on the top two to make it easier as we go on. And then lastly, he also mentioned to us that the thickness of somebody's skin is very dependent on their BMI, and that it's not always the same for each person.
And he was saying that with the pigments, if it's more realistic, with a Caucasian person, it's a little bit easier to see the veins and see inside the person compared to a darker skinned individual. So that's why he was saying, make sure that we can try and do different skin pigments.
And then last thing, this also told us like some changes that we need to make for example, the sketch that we made was called, he said that our size was too small. And it basically showed us what we need to do in the future with that. And here are some examples of medical mannequins they showed us. Some of them were just the basic for the lungs, and other ones were basically showing how the skin was. And you can see how thick the actual skin is in comparison to my phone. And then the skin, it wasn't very it didn't have a lot of friction, and it wasn't movable. It was very hard to actually compare it with actual skin.
This is a SolidWorks drawing of the frame that we printed out. When we get the PDMS and the Silicard, we're going to pour it inside the frame and start making our layers of different skin. The frame size is universal. It works on infants, children, and adults. However, on the adult one, it shows the target area. It doesn't give the students a chance to find the area in the torso.
And this is the printed frame. This is just our tentative sketch.
Mm-hmm.
Our budget, we have $2,000 right now. We spent tentatively, after some conversation. It's about $506.87, which leaves us with $1,493.13 left as of right now.
This is our protocol on how we're going to make the different layers of skin. So first we're going to prepare 40 grams of PDMS. We're going to start with the stick. We're going to put it in an 80 degrees oven for 35 minutes. We're going to use a razor to cut out the PDMS and repeat the step for EcoFlex 30 and EcoFlex 50. Before the last layer dries, we're going to put a leather vinyl, like a piece of fabric, to mimic the skin on top.
So some of the testing that we're doing is porosity testing, indentation and static friction testing, biomechanical image analysis, and that measures Young's modulus. And then we're also going to use, well, it's a tentative thing that we might use the scanning electron microscope, which is a SEM, to analyze the artificial skin that is made.
Okay, so both the characterization methods and the protocol are both under development. As we continue our work and actually and get our materials, we'll change and tweak it as see fit. So upcoming work, we see that we need to actually 3D print all the layers using the updated SolidWorks drawing that we will make. And as mentioned earlier, we will focus on the epidermis and dermis layer. And then later we need to create more of a framework for our target subject and make sure it's the correct size that we leave for the actual chest tube insertion area. And then in order to gain a better idea of what our product needs to look like, we want to go to the simulation lab in UNC Chapel Hill and actually see what their lab, see what mannequins they have. And then lastly, we want to do prototype testing and do a decision matrix for the characterization testing to see which ones are our top 3 or top 4 that we actually want to keep later on. And this will also be dependent on what actually materials we have, what actual tools we have to actually test the skin.
Questions?
Questions or comments?
Let's have a,
Good.
so is your thing supposed to be for just the mannequins or for humans too?
It's supposed to be for the mannequins.
Oh.
We're only sticking to one thing right now, so it's just the mannequins.
So if you don't mind me asking, how did you guys come across that recipe for the skin?
I did research over the summer at the University of Nebraska, and we worked with microfluidic devices. We made PDMS, and that's really how I came up with the recipe.
Other question?
Dr. McCullough?
we always know.
Okay, so tell me a little bit about what you hope to learn using SEM on your sample.
So SEM just allows you to look deeper into,
The electrons.
yeah,
Yeah.
to just make it more realistic and see. Because as Dr. Joyner was talking about, like, our skin has like give to it, and just kind of doing another testing versus just a physical eye test of, oh, it gives it just something else to do.
So you want to? I mean, is it going to be one of those things where you're comparing molecules, or? I guess I'm not seeing what the SEM is going to add, and I don't know from a cost and time perspective.
Well, we told Dr. C we were going to come up with a couple of methods that we could discuss, and actually our meeting is on Wednesday to kind of like break these down and see what's really realistic and what's not realistic. We just looked at prior research and saw that they used an SEM, and so we were going to see how it might benefit us as well.
As you have that conversation, either with him or even for you all, just kind of keep them. So like, I can see where porosity is important because skin, and then indentation is important because that's going to tell you about what you need to do for the tube and even your mechanical part. So just be sure that you have a very clear outcome for what you're going to do with your SEM testing. Okay. And then in terms of the, so now your new size, so I understand the thickness. So are those generally the dimensions for the patches? That's going to be big enough?
Yes,
It is.
we actually you talking about this one in particular?
Yes.
Okay, yeah. Yeah, we actually, when we went to Dr. Joyner, measured this on the side of the mannequin, and as Alexis I think was saying, it's universal, but if you put this on an adult size mannequin, it's going to tell the
The students.
Yeah.
Right.
yeah, versus if you're trying to train them that he wants it a little bit bigger.
Yeah.
So we need to determine, are we making this just for a baby mannequin or a young adult or
Okay. So
Or-
that's still working
So that's what we have to
Yeah.
specify going further. Because the size that he had in there originally, he said that was too small. And then for another thing to add, shortly is where is it? The characterization methods was called. So we're also going to be asking the UNC Chapel Hill simulation map what they actually use to actually measure the skin, and then also we're still reaching out to other companies as well to see what their characterization methods are.
Questions, comments? Thank you. Volunteers?
Hey guys.
Hello.
Thanks.
back to my camera.
So, I'm Courtney Wallace,
I'm Joshua Keku.
And I'm Tyra Fultz.
and we are Life for Neonates.
So our problem statement is essentially the same as before. The small size cannula diameter is still too small for the machine, for an ECMO machine to support the heart and lung functions of a less than 34 weeks gestation baby. And this makes it a high risk to utilize ECMO. So for our timeline, okay, so in January, we got to have a conference call with Dr. Pranikoff from Wake Forest Hospital, who was able to put us into contact with a doctor at Wake Forest Baptist. And January 30th, we met with our head here of our project, Dr. Sun, to update him on the work that we've done thus far. On Friday, we were able to meet with Dr. Bernard Burns, who Dr. Pranikoff got us in contact with, and we were able to visit Wake Forest and actually go to the ECMO area in the hospital for adults and see a patient on ECMO, as well as go to the pediatric unit and view a ECMO machine for babies. Later on in February, we plan on working with other clinicians. So we didn't put this on the timeline yet, but because they just emailed us. But we have a clinician that the Extracorporeal Life Support Organization also put us in contact with, who's from Michigan, who's actually where ECMO actually started. So we're going to be having a conference call with him in the later on week. And then we also have another doctor who we got in contact with who will be putting us in contact with other pediatricians. We plan on getting a drawing of the ECMO design or an ECMO design so that we can start putting something on SolidWorks and actually testing things out and having a 3D print of our design created by late February, and then in March being able to test that 3D printed design. So for completed tasks, we've gotten our conference call with Dr. Pranikoff. We received a polyurethane tubing so that we can kind of see what the, because that polyurethane is the actual tubing that, or material that they usually utilize for cannulas. So we can see how it works and how it bends and everything like that. And we met with Dr. Bernard Barnes at Wake Forest and got to tour. And we actually received some items from him that we will show you guys later. Challenges faced. Challenges was finding a clinician, But since we're now getting all these emails from different clinicians, that's not really a challenge anymore. Creating a design that is small yet has sufficient and efficient flow, because the job of a cannula is to support the flow of the vein and bring blood from the superior and inferior vena cava and back into the atrium. And so making sure the design we create does not kink, because you want no kinks, because that will disrupt the flow of blood. Thinner walls that won't compromise the integrity of the tube. So we want to have thin walls for the baby, but thin walls can cause kinking. So that will also be a very big challenge. Understanding the fluid dynamics equations and how they coincide with our tube design, because it's very vast. And yes, we've had classes in this particular area, but actually applying it is a whole different beast. And making sure our cannula size works for the majority of our market. And we do recognize that our market is very small, and that cannula, the doctors choosing the cannula size is dependent upon the baby's size, weight, and everything like that. So we want to have a cannula that it works for the average amount of patients that are going to utilize it.
So from our first meeting, which was with Dr. Pranikoff, so he's a professor of surgery and pediatrics, and he's the surgery in chief at Brenda Children's Hospital, which is at Wake Forest. So he sent us 4 articles to read, most of them being from University of Michigan, because that's where the whole ECMO design came about and was started. He suggested that we do a double lumen cannula. Most infants use the VV method, which is the Venius method, goes through the vein. They suggested that the size be 8 to 10 French, and to focus on the maximum flow and resistance, making the inner wall thinner. The tube, he let us know that the tube actually goes 6 to 8 centimeters in the vein, and Wake Forest only gets about 30 patients on ECMO a year, most of them being adults. So we have to focus on how we're actually going to get the cannula to downsize for a neonate. And we need to ensure that if we're making the wall thinner, that it doesn't affect the integrity of the actual cannula. And he suggested us, most cannulas use stainless steel. But most cannulas use stainless steel on the inside. That's the wiring that you'll see when we pass it around. But he suggested that we used a different material called nitinol for the tubing to help with the integrity. On Friday when we met with Mr. Bernard Barnes, he's an ECMO educator there. The program for the ECMO has been, he said, it's been there since 96, and he's been there since 97. So he definitely had a lot of experience with it. So when we walked through the NICU and the intensive care unit at both, not at both, but at Wake Forest, he suggested that we use a roller pump method that's what they use currently for neonates, which is a roller pump method. And they use a 1/4-inch tubing to help the fluid flow. So that's not the one. He suggested that we use wire reinforcement, which allows the walls to be made thinner, which is the wiring you see in the cannula now. He told us about the insertion site of the tube and where it's likely to kink up when it's being inserted. The doctors would like to see the wall as thin as possible, the cannula as short as feasible, but the Venius tube as big as possible. And he also let us know that the market is really small for this, but and big drug companies aren't looking towards it, but doctors are doing their own research to try to solve this problem. And then this is just a picture of the ECMO machine that they use in the NICU.
All right, and here are a couple of things that we plan on accomplishing within the next month. We want to get like we said earlier, a rough draft of a new innovative design of the cannula tube that we plan on creating. And we need to better understand the equations for fluid flow and accurate flow through the tube for this. We're working on getting a tour of a facility with an ECM machine, but that's kind of already been accomplished. Purchasing a double lumen cannula Since we got one from Wake Forest, I guess we don't really need to worry about that anymore. And then we're considering creating a design for testing pressure flow characteristics. Ordering lists of equipment needed to test those parameters is something we're working on. Analyzing cannula tubes given to us from Wake Forest and beginning to sketch up a design. And here's our budget. We started off with $2,000. We've only spent roughly $20. That's because we kind of had trouble in the beginning figuring out what we actually wanted to do and what we would actually need. And some possible future orders would be a pressure manometer, flow meter, a centrifugal pump, and a testing bottle. And our remaining budget is about $1,980.
Questions, comments, suggestions, concerns? Could you go back to your, I guess at the beginning, kind of summarize as your problem? Okay. So ultimately here, you're trying to address this by, I guess, what's your concept for your solution, or are you still deciding on the concept?
Making the tube smaller, making the cannula tube smaller, because this one is 16 French, and the one that was passed around is 19 French, but they're still way too big for like a neonate that's 34 weeks. So it's more so of trying to like downsize it so it will, be able to work for the 4 neonates. And we've also seen a 12 French one, but that one, Mr. Barnes was still saying that it was still too big for neonates. They have trouble getting it in without damaging too much.
Yeah, and
in the vein.
The French measurement is related to the diameter of the actual tube.
Okay.
Yeah.
So ideally, the overall design itself, trying to keep that as much as similar to what it is now, but just reducing the size, and then all these other things that he threw at you,
The
in
flow
terms of
and
the
stuff,
flow,
yeah.
the knit, and all this other stuff. It's a lot.
Yep. Sure is.
And then in terms of, so it's all about diameter. That's the biggest thing you're trying to tackle. The length is not necessarily.
The diameter needs to be smaller, but yet they're like, you don't want to compromise certain things for the flow because you still need it to support the pump flowing of the blood. And with the double lumen, like the largest one is 12 or 10 or 12.
The smallest one?
Smallest one?
Yeah.
12? Yes. So with that, he was just saying that it should be a little bit shorter and things like that. But when you're messing with the length of the design, that directly impacts the flow. So we have to take into consideration all those things, which is why we're going to start getting on SolidWorks and testing if we can test it out through that, and then learning how to better make it, because just writing down the equations doesn't really make it click, but seeing it will probably help us to understand how our design will actually work.
So you found the fluid flow tutorials on SolidWorks? Work those yet?
We need to find those.
If that doesn't work, see what COMSOL has. It looks very similar to SolidWorks analysis, but it's multi-physics and it's a little bit better on thermal and fluid flow kinds of modeling that you need to do. And for a relatively simple shape, you can probably just draw it in COMSOL and CLM, SOL.
CLM, SOL, got it. Yes, Tanisha.
I just want to know, like, how are y'all gonna test it to know, like, that it works for neonates? Like, the ones you passed around, you said they're like too big or whatever. So, the one that you guys are gonna design, how, like, are you gonna test it?
Well, we can't test it on a baby, so that would probably have to be with the simulation thing, like Dr. McCullough just gave us with the COMSOL, with the flow, and actually testing it that way.
It'll be more theoretical.
Yeah. Because we can't get a baby. I wouldn't want my child to be,
There may be some other pseudo-physical things you can do in terms of just setting up a pump system. You just make a smaller put it inside of a tube that's about the same size. And see
Yeah,
if it
that's
does.
one.
There are
the thing that
materials.
we wanted to get ordered and stuff like that.
Other comments, questions? Good. Thank you. All right. Well, thank you all to all of you who presented today. Good job. We're off to a good start, I think. Like I said, keep plugging along. Hopefully, all the questions that you received today, you make note of them. And even if you didn't present today, but there are some questions that